Jump past question 2001, question number 48. Energy losses through AD currents are reduced by using A. Low resistance wires, B. Insulated soft iron wires, C. Few tons of wire, D. High resistance wires. AD currents. AD current. Before we can do justice to today's question, we need to understand what AD current is all about. AD current is an effect due to electromagnetism and Lenz's law. Electromagnetism and Lenz's law brings about AD currents. AD. Okay, see what I mean by that? It was observed by Michael Faraday that when you pick a magnet and you get coils of wire, you make relative motion of the magnet across the wire. Get a magnet, move it across coils of wire. Then you induce EMF in the wire. Automatically, the wire will experience a kind of a flux. Okay, that's what I mean by electromagnetism. This time we're converting magnetism into electricity. Converting magnetism into electricity. Just pick a magnet, get your wire, make a coil out of it, put the two ends to a light bulb, then make relative motion of the magnet across the wire. Then the light bulb turns on. Although, depending on the load. Although, depending on the resistance of the light bulb. Okay, then let's observe. Then, when Faraday discovered that law, the law of electromagnetism, Lenz made a contribution to that law. Lenz contributed that when a magnet moves across coils of wire, that the induced current in the coil goes in opposite direction to the changing magnetic field. Taking attention. When your motion with a magnet causes a wire to have energy in it, that the current induced in that wire goes back to fight your motion. And the current is what we call AD current. That current that wants to go back to stop you, to hinder the motion, is the AD current. This happens in most electronic components. A good example is a transformer. A transformer, observe. In a transformer, we have something called a core, iron core. Then we have our primary windings, then connected to a source. Okay? Then we have our secondary windings connected to a load. Load source. Okay, observe. This is what we're saying. So the current starts from the primary coil. When the current goes through these coils, then something happens at the secondary coil. The flow of current here changes these wires to electromagnets. Therefore, it's also a magnet. Recall what we discussed on magnetism. This is also electromagnet. It's also a magnet. Why? Because current is going through it. Therefore, this becomes a magnet. So this magnet is also changing because current involves flow. It flows through the wires. So therefore, this is also a magnet. So this is also a changing magnet. It will induce EMF in the secondary coil and also on the core. And instead of going this way, the current will initially want to go that way to hinder the motion. Instead of going that way, it will initially want to go that way on the wires to hinder the motion, because this induces EMF in the second one and also on the iron core that connects the primary coil and the secondary coil. So that current that wants to hinder the exact source that gave rise to it, that's our AD current. AD current. And as a result of that, we'll call it loss. We'll consider it loss because it brings about reduction in the cause that brought about its existence. The motion wants it to go forward and it's taking it the other way. So it will cancel some of the motion. It brings about retardation. So we'll consider it loss. That's why we use the term AD current loss. Yeah. So this is a kind of law of nature. Every meaningful thing, there must be a sort of sacrifice. So the AD current wants to stop the exact source that wants to give rise to it. Okay. So we'll talk more on this AD currents. But for now, it's considered a lux in transformer and some other circuit components. It's a lux here in the sense that it fights the source. It reduces the flux that the original source wants to give the circuit or the secondary coil. Then observe, In order to reduce this eddy current loss, we play smart. The first thing we do is to make the core and the wire very thin or soft or thin. Why thin? Because the thinner the wire, the fewer the number of charges on the wire. The thinner the wire or the soft the iron core, the fewer the atoms and the charges on the wire. But the thicker, the more the atoms. So the first secret to making it soft or thin is to control the number of charges. Then the next thing is insulating. Insulating the soft iron core. The soft iron core has to be insulated because when it's exposed, then there is easy interaction. But when insulated, you damp the interaction. Instead of the currents inducing power in the core and the secondary coils. So we've reduced some of the losses by covering our wires, by insulating the wires. So some of the losses have been controlled. That's why we also do insulation. Then both actions we've done here is considered as lamination. This is the buzzword for what we've said here. So let's go back to the option. We can see that the best option there is option B, insulated soft iron wires. Insulated and soft iron wires will bring about reduction in eddy current. And one word for that is lamination. Lamination. Thank you. Please stay tuned as we push ahead.